Hello everyone, and welcome back. Today we're going to continue our exploration of vector spaces and introduce a concept known as the basis of a vector space. Later on, we're going to talk about a very important algorithm that can construct bases of vector spaces where that basis has some particular structure that can be very useful to us. So, what is exactly a basis of a vector space? So let's assume that V is a vector space, i.e. it satisfies those 10 properties that we discussed before, and let's assume that the dimension of V is equal to n. Then a basis of V is just a set of n independent vectors all belonging to V. So if you know anything about independent vectors and sets of vectors, we should know already that if we have n independent vectors of a set V and the dimension of V is equal to m, then we should know that the span of that set is equal to the entire set, right? So we can say that if B is a basis of V, then that means B is a set of independent vectors of V. And we're actually going to be representing this as B subscript V. Then the span of that set, B sub V, should be equal to the entire space, V. Right? So just some trivial examples. For example, if you want to span all of R3, what would be a good basis for R3? So for example, we can choose the set S1 to be equal to the set of vectors 1, 0, 0, 0, 0, 1, and 0, 1, 0. And we should already know that these are three independent vectors of R3, and hence the span of this set of vectors S1 should be all of R3. Right? So since we have three independent vectors of R3, and we know that the span of S1 is equal to R3, and moreover the dimension of R3 is equal to 3, and the size of S1 is equal to 3, then with all these things intertwined with one another, then we have that S1 is a basis of V equal to R3. Now the next question becomes, well, is it the only basis of R3? And of course, no. For example, I can choose another set, for example, S2, to be equal to the set of vectors 1, 1, 0, 1, 2, 2, and 1, 1, minus 1. So on the surface, you may not be able to quickly realize that these vectors are independent of one another. Maybe one is dependent on another two, or maybe two are dependent on one of them, right? Because the span of S2 could be a one-dimensional, two-dimensional, or three-dimensional subset of R3, and all of them are non-zero, so we can't get a zero-dimensional subset of R3 in this particular case. But what we can do is we can look at the reduced echelon form of the columns of this particular set, and we can find that the reduced echelon form is going to come out to 1, 0, 0, 0, 1, 0, and 0, 0, 1. So if that is the reduced echelon form and we have three, that means we have three independent vectors in S2 from R3. So since this implies we have three independent vectors of R3, since the rank of the associated reduced echelon form matrix is equal to 3, that means that S2 also is a basis of R3. Right, so if that's the case, we can easily come up with the following conclusion, that the basis of a vector space V is not unique, especially if the dimension of V is not equal to 0, because one can show if the dimension of vector space V is equal to 0, the basis is to some degree unique because you can only have the 0 vector in that particular set. Right, so with that being said, let's make a quick note here. Some bases or basis sets are better than others. Some are better than others. For example, if we look at that first set we gave, which was 1, 0, 0, 0, 1, 0, and 0, 0, 1, what advantage does this set have over the other set that I gave? Well, one observation is that, for example, all of these vectors are unit vectors, and each of these vectors are pairwise orthogonal to each other. So we have a set of 3 unit vectors that are pairwise orthogonal to each other, so that means this set is an orthonormal set. So it's an orthonormal set. And since we already know that S1 is a basis for R3, that means we have that S1 is an orthonormal basis of R3, right? So what's so special about an orthonormal basis? Well, if you sort of think about what a basis means, well, the span of these vectors is equal to R3. That means every vector in R3 can be represented as a linear combination of these vectors, right? So, for example, what we can do is we can choose some vector, let's say 3 minus 2, 1, belonging to R3, and we can represent this vector as a linear combination of these 3 basis vectors, right? So that means there exist these constants ak in the set of real numbers such that 3 minus 2, 1 is equal to, for example, a1, 1, 0, 0, plus a2, 0, 1, 0, plus a3, 0, 0, 1. So what do you think these numbers A1, A2, and A3 should be? Well, just by observation, you should be able to guess that A1 needs to be equal to 3, A2 needs to be equal to -2, and A3 needs to be equal to 1, because that's pretty much the easiest decomposition of an Rn vector that you could possibly have, i.e. these 1, 0, 0 type of vectors in terms of linear combinations. But if you were to choose the other basis, for example, and we were to choose the same exact vector, say 3 minus 2, 1, there of course exist these constants, say, let's call them B1, B2, and B3. And let's choose the same exact vectors, 1, 1, 0, 1, 2, 2, and 1, 1, minus 1. We know that these vectors form a basis for R3. Therefore, these constants, B1, B2, and B3, all do exist. But it's not trivial as to what they are, right? For example, we would have to do, for example, a system of linear equations, because how would we actually find those B1, B2s, B3s? So we would set up systems of equations, for example, 1, 1, 0, 1, 2, 2, 1, 1, minus 1, times B1, B2, B3, and that should be equal to 3 minus 2 and 1. And since we already know that these vectors form an independent set of 3 vectors from R3, we should know that this matrix, if we call it A, is non-singular, i.e. the determinant is not equal to 0. Therefore, the inverse of this matrix exists, and hence this solution B1, 2, 3 is unique, so we can find those numbers, but we can't easily identify them as we did, for example, this beautiful orthonormal basis of 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? And with those things, of course, you should be able to figure out a couple observational corollaries, let's say. So let's assume that, for example, BV is a basis for V, and S is a set with the size of BV not equal to the size of S. So for example, if V is a vector space with the dimension equal to 5, then that means the size of B will also be equal to 5. And if we assume that S does not have the same exact size of BV, that means what? That means the size of S has, for example, 6 vectors, 7 vectors, 4 vectors, 3 vectors, maybe 0 vectors, the empty set, right? So one should be able to prove, at least in terms of logic, that if BV is a basis for V and S is a set with a different amount of vectors as BV, then it is impossible for S to also be a basis for V. Now, does it work the other way around? The answer is, of course, no. For example, you could have two different sets of the same exact size. One is a basis and the other is not a basis. A very easy counterexample to that, for example, would be, for example, S1 to be equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's obviously a basis for R3, but if we choose another three vectors, for example, 1, 1, 1, 0, 0, 2, 0, 0, and 3, 0, 0, very trivial example, that's just going to span a one-dimensional subset of R3, but they have the same exact number of vectors, but this is not an independent set. Right, so those are just some easy observational things that you should understand when it comes to establishing or finding or verifying bases of vector spaces. So up to this point, we've already established that bases of vector spaces are not unique, and some do have some advantages over others. So one could ask, well, let's assume that we have a not so nice set that forms a basis for a vector space. Is it possible to transform that particular set of vectors into another set of vectors that has some nicer properties than the one that it had before? So if your goal is to form, say, an orthonormal basis of a vector space from a set of vectors that is not, say, an orthonormal basis, then there's a method referred to as the Gram-Schmidt process, or the Gram-Schmidt algorithm, that can transform a set of n vectors that are independent into a set of n independent orthonormal vectors. Okay? So let's just walk through this example, and actually let's go with that set that I mentioned before that we've already verified as a basis. In particular, let's do 1, 1, 0, 1, 2, 2, and 1, 1, minus 1. Because we already know that this is a basis for R3, but it's not an orthonormal basis for R3, right? So this is a basis for R3, so let's transform it into 1, right? But it is not an orthonormal basis, right? Because obviously they're not unit vectors, they're not pairwise orthogonal to each other, so yeah, those are easy to verify. All right, so before we get into that, let's just recall a property that we discussed some time ago, and that's the projection of vectors onto vectors. So the projection of vector u2 onto vector u1 is going to be equal to u2 dot product u1 divided by the norm of u1, the quantity squared, times the vector u1. Right? So that's the projection of one vector onto another. So let's just draw a little picture just in case you don't recognize that. So let's assume that this is u1. Let's assume that this is vector u2. So the projection of this vector is going to be this little thing. Right? So that right there, that's the projection of u2 onto u1. Right. Just some important things. What is this particular vector here? So that is going towards u2 away from the projection of u2 onto u1. So that is the vector u2 minus the projection of u2 onto u1. Right? So those are just some basics that we discussed some time ago, but we didn't really get into applications, but the Gram-Schmidt process is one of the most important applications of projections, at least in the elementary linear algebra perspective. All right, so the first thing that we need to do is create our first unit vector. So let's assume that we want to make this our first unit vector. That should be very, very easy to do, right? So what we can do is we can define q1 to be equal to the first vector divided by its norm. All right, so that always is going to form our first unit vector, right? So if we represent our first vector in terms of q1 from u1, then we can actually represent this projection in a slightly different way. So that means the projection of u2 onto u1 is actually equal to what? So that means this is going to be equal to just Q1 dot product with U2 times Q1. And you could also write that as Q1 transpose U2 Q1, or you could also write it as U2 transpose Q1 times Q1. Either one, of course, would be equivalent things. Right? So the next thing I want to define is what I'm going to represent as U2 star, right? So we have our first vector U1, and now we've normalized it and we've called it Q1. Now we need to have another vector that is orthogonal to Q1. And U2, our second vector in our set, is not necessarily orthogonal, else we wouldn't have to orthogonalize it. So the orthogonalized version of U2 with respect to U1 is going to be called U2 star. So I'm actually going to call this U2 minus Q1 dot product U2 Q1, or equivalently, this is going to be equal to U2 minus the projection of U2 onto U1. In particular, it's technically Q1 now, right? So one should be able to prove from this definition that U2 star dot product with Q1, which is of course the same as Q1 dot product with U2 minus Q1 transpose U2 times Q1. So that's a vector, that's a scalar, that's a vector. This is always going to come out to 0 for any U2, even if it's the 0 vector. That is, if we have a vector Q1, and it doesn't have to be a unit vector, but we of course are forcing it to be, and we define U2 star as this particular vector, then that always creates an orthogonal set. Not necessarily an orthonormal set, because U2 star not necessarily is a unit vector, but at least U2 star is orthogonal to Q1. So we have Q1, a unit vector. Now we have U2 star, which is orthogonal to Q1. So we can, for example, define Q2 to be equal to U2 star divided by the norm of U2 star, right? And then we can consider the set S, which is consistent of Q1 and Q2. So Q1 by construction is a unit vector. Q2 is of course a orthogonal vector to Q1, and of course if we normalize that, that still preserves the orthogonality between these two vectors, and by definition Q2 now is a unit vector, so that creates an orthonormal set, which is the goal of the Gram-Schmidt process. So let's go ahead and turn to our numerical example and sort of see how those numbers work out. So let's start with the first vector that we had in our set, which was 1, 1, 0. It's very easy to show that the norm of this particular vector is just going to be equal to the square root of 1 squared plus 1 squared plus 0 squared, which is just going to be equal to the square root of 2. So once we have the norm of the first vector, then we can very quickly define Q1 to be equal to 1 divided by the square root of 2, 1 divided by the square root of 2, and 0 divided by the square root of 2, which we know to be equivalent to writing square root of 2 over 2, square root of 2 over 2, and 0. So that is our very first vector of our orthonormal basis of R3. Now we're going to find our U2 star, which by definition is just going to be equal to U2 minus Q1 dot product with U2 times Q1. So let's recall what U2 was. So U2 was equal to the vector 1, 2, 2. So now we need to find the dot product of U2 with Q1, or you could do the dot product of U2 with U1 and then come back. That's perfectly okay. So if we do directly U2 dot product with Q1, that's going to be equal to what? So you should be able to dot product that vector with no issues. And you can find that that's just going to be equal to 1 divided by the square root of 2 plus 3 divided by the square root of 2 plus 0, which is just 3 over the square root of 2, which is equivalent to 3 square root of 2 over 2. If you work with the left or the right versions of Q1, either one, you'll get the same exact answer. So now that we have the dot product, which represents in some sense the angle between them, now we need to take that scalar and multiply it by Q1. So once we have that, we have the Q1 transpose U2 times Q1. is going to be equal to, let's go with 3 over square root of 2. I think that's a little bit more easier to work with, times q1, which is 1 over square root of 2, 1 over square root of 2, and 0. The only reason I'm keeping my radicals on the bottom is so that those radicals sort of cancel each other out quite nicely. And we have 3 halves, and 0. Once we have that, then we need to change our direction, do u2 minus that vector. So we're going to have u2 star, which is going to be equal to u2 minus 3 halves, 0. And once we use that particular u2 and get our common denominators, we're going to have minus 1 half, positive 1 half, and 2. Once we have our U2 star, now we have an orthogonal vector to Q1. Now the last thing we have to do is normalize U2 star. So the norm of U2 star is just going to be equal to the square root of minus 1 half squared, 1 half squared, and 2 squared. And we should be able to see that that's just going to be equal to the square root of 1 plus 16 divided by 4, which is the same as 3 square root of 2 over 2. So once we have the norm of U2 star, now we can define Q2, which is just going to be equal to U2 star divided by the norm of U2 star. So one can find, once you rationalize all of those things, that's just going to come out to minus root 2 divided by 6, root 2 divided by 6, into root 2 all divided by 3. All right, so that gives us our second orthonormal vector, but now we need our third. So keep in mind, U2 star was equal to U2 minus Q1 transpose U2 times Q1. So what would U3 transpose, or U3 star, defined to be? So one can show that that's going to be U3 minus Q1 transpose U3 times Q1 minus Q2 transpose U3 times Q2. And one should be able to prove that U3 star is orthogonal to both Q1 and Q2. So using that formula and going through these same exact things, of course it becomes a little bit more tedious, and then normalizing that particular vector, you should be able to find that Q3 will come out to minus 2 divided by 3, 2 divided by 3, and minus 1 divided by 3. Generally speaking, the formula for constructing these orthogonal vectors can be calculated via the formula UK star is going to be equal to UK minus the sum from j is equal to 1 to k minus 1 of qj transpose times uk, which is a scalar, times the vector qj. So for our particular example, we have built from the original set the following set: root 2 over 2, root 2 over 2, 0, minus root 2 over 6, root 2 over 6, and 2 root 2 over 3, and minus 2 over 3, 2 over 3, minus 1 over 3. And one should be able to verify that this is an orthonormal basis of R3 as designed. The last thing I want to discuss today is some theoretical aspects associated to the bases of vector spaces and the resulting result of the Gram-Schmidt process, in particular an orthonormal basis. The first is this. If S is a set of n orthonormal vectors, i.e. an orthonormal set of vectors for which forms an orthonormal basis for S, then S can be a basis for some n-dimensional vector space, right? So if you have a set of orthonormal vectors, that can be a basis of an n-dimensional vector space. You just need to make sure that it's the vector space that you want. But typically, if you have a set of n orthonormal functions, then you should be looking for an n-dimensional function vector space in particular. Now, does it work the other way around? The answer is, of course, yes. So if you have an n-dimensional vector space, then you should be able to find always a set of n independent vectors, more so a set of n orthonormal vectors as well. right? So how can one justify that you can always find a set of orthonormal vectors? Well, we know we should always be able to find a set of n independent vectors. That should not be debatable at this stage. Right, and if you can always find a set of n independent vectors, you can always apply the Gram-Schmidt process to transform that into an orthonormal set. So that's pretty much the logical flow of how to prove such things like that. Now, if Q is an n by n orthonormal matrix, then the columns of Q can form a basis for Rm. That pretty much ties together with this first theorem that I stated here, but this ties into, okay, Q is now a matrix, the columns of it form an orthonormal set, and of course, if it's an orthonormal set, it can be represented as a basis for an n-dimensional vector space, in particular Rn, since we're working with a matrix of real numbers. Now I need to ask a very important question that a lot of you may be asking, and that is, so what? So let's sort of go into a discussion that I briefly mentioned a little bit ago. So let's assume that U1, U2 down to Un is a basis for some vector space V. Then for all x inside that vector space V for all vectors, there exists this sequence of numbers xk, which should be a subset of the real numbers, such that x can be represented as a linear combination a1u1 plus a2u2 all the way down to an or more compactly the sum from k is equal to 1 to n of ak uk. So scalar and vector there. Right, so the next thing that we need to find is, okay, what are those xk's? So what are the ak's? Right, that's not always obvious, that I already mentioned before. So even though we do know what U1, U2, and UN are, these ak's are not necessarily trivial. Right, now let's assume instead that if Q1, Q2 down to Qn is an orthonormal basis of V. And technically, these could be transformations of one another. For example, we can always transform this set into this set via the Gram-Schmidt process, so that's not a big issue. So let's assume that Q1, Q2, and Qn are the results of the Gram-Schmidt, and in particular is an orthonormal basis of V. Then again, for all x in V, we can represent x as a linear combination of these vectors, right? So in particular, the sum from k is equal to 1 to n of, again, some constants. Let's call them, for example, bk, qk. Right? But again, we need to figure out, what are these bk's? What are these bk's equal to? Right? Now, if qk is the vectors like 1, 0, 0, 0, 1, 0, those are trivially the elements of the vector x, right? That's not debatable. But again, for example, the example we did before, just because it's an orthonormal set doesn't mean those numbers are pretty, right? So that's a very important thing to keep in mind. So let's sort of think about how we would find these AKs in the non-orthonormal world. So we would, for example, construct a matrix U, which had the columns U1, U2 down to UM. Our goal is to find those constants A, A1, A2 down to UM that produce this vector X, for which we're trying to represent as a linear combination of these vectors. So U is a basis, that means the inverse of U exists. So we're going to have A is equal to the inverse of U times X, and U is just a generic n by n matrix with random coefficients, generally speaking. So, that inverse procedure probably is extremely annoying, even with, for example, like a Gaussian elimination or whatever other methods you might have at your fingertips. But if we approach it via an orthonormal set, so what do we have here? So we're going to throw all the vectors Q into a matrix. Let's call it, for example, Q. And we want to find those numbers B that make that true. And again, we're trying to represent X as a linear combination of those vectors. So in that particular case, again, the columns of Q form an independent set. So the inverse of this exists, and we can find that B is just going to be equal to the inverse of Q times X. So we get that particular result. But if the columns of Q is an orthonormal set, that means Q is an orthonormal matrix, and the inverse of that square orthonormal matrix is precisely equal to the transpose of that matrix, which is very, very trivial to get. So if you look at the expansion of those things, and since that gives you the coefficients of B, so you can look on, for example, each of those rows, you should be able to find that this is just going to be equal to X is equal to the sum from K is equal to 1 to M of QK transpose times X times QK. Some people also will write it as the other way, some k from 1 to n of x transpose times qk times qk. Because keep in mind, that's just another way of writing the dot product of x with qk, and that's just another way of writing qk dot product with x, which is equivalent, so those are very, very easy to get. So, if you want to find the coefficients of the linear combination, if you want to use orthonormal basis, you just need to take the dot product of the vector x for which you want to represent with each of those orthonormal basis vectors, and that will give you your linear combination coefficients. So those are the basics associated with basis of vector spaces and the Gram-Schmidt process, which can take any set of independent vectors and turn them into an orthonormal set of vectors. Hope you enjoyed, and I'll see you in the next video. Take care.